I'm standing here in the interior court of TUM, and as you can see around me there are few organic materials. Why is this so? The only organic materials that we find are some trees and some flowers. The flowers are pushing towards the sun, so their trunk has a direction. They are isotropic, and other organic materials might be anisotropic or isotropic. But why are we not finding more organic materials around us? Well, two reasons. They burn and they rot when they get too much humidity. And over time they decay, as you can see in plastic boats or also in wooden structures as well. So they need maintenance, and much more so as most of the metallic and the mineral materials. Another specific characteristic of organic materials is their elasticity. Here you can see I can bend the rod of this flower here in a substantial way, which would not be possible for mineral materials, for example, or for metal, maybe if it gets thin enough. But the elasticity module is much higher for metals and for minerals than it is for most organic materials. As you can see in the suspended bridge behind me, it's made out of metal. And if I would want to make it out of plastics, for example, I would have to reinforce the plastic with another material. Wood-based would be possible if the main load was in compression, because it is too difficult to connect different wooden elements in tension. So we normally use metal as a connector for wooden particular pieces. Particular performance of thermoplastic plastics is that you can make foams out of them. So foams that could be used for facade insulations, like the one behind me. As you can see, you can use wood as seat in open air, but after a certain time, exposed to water, it decays and then disintegrates. So this is one of the major disadvantages of organic products, and especially wood. As you can see in the building behind me, the windows are made out of wood, and the siding of the facade is made out of extruded aluminum. On this motorcycle behind me we have organic and metallic materials. Metallic materials are used for the tank, for example, or for the engine parts, or for structurally very solid parts like the wheels or the discs, and where it has to be comfortable. There we have the seat, which is covered with the plastic liner, and there's some sort of foam behind that to sit comfortably. And we have footrests, or we have tires which are made out of elastic material. The trees beside me have a specific direction. They collect water in the ground and then lead it up to the leaves that are exposed to the sunlight. So this specific direction is expressed in the section of the wood itself. So here I have a material which is called firewood. So it has a wooden surface, a veneer, and it has a gypsum-based core that contains a lot of water and thus becomes fire resistant. So combinations of different materials are also a topic, but I'm not getting too much into detail because the variations are infinite. So for plastic materials, we have long chains of molecules. So many of these plastic materials are called poly something because there are so many of these molecules. And then I have different types of plastic materials, one being duro hard plastics, mostly resin based. And then I have elastomers, and third would be thermoplastic. If you heat them, then the chains of molecules would change their position, and when they get cold again, they would stay in this position. Elastomers consist of very long strands which are connected at fewer spots. So there's a lot of elasticity for movement inside the molecular structure. And duroplastics have a very tight grid of connections, so they are much more difficult to move than the elastomers would be. Typical elastomer would be rubber bands, and duroplastics would be resin-based boat shells or things like this. And thermoplastic are mostly all kinds of things that could be put in a form in one way or the other. Like, for example, this ruler here I'm holding in my hand, or parts of this pencil. In terms of wood or wood-derived products, we have the tree trunk, where we cut off the upper part and we cut off the lower part. And so there's only the tree trunk that will be used as construction wood. And then this tree trunk can be cut into boards, and then these boards may be reassembled as, for example, in a glulam section, or they might be used as traditional lumber. And so we have the growth structure of the tree on the inside of the full wood section. So what we could also do is to peel off the trunk in a way of producing veneer, and then we could have one layer of plywood in this direction and then the next layer in the other direction. So it is sort of brought in a 90-degree angle, then reassembled to form plywood. And we could also cut it in smaller pieces like strands, and then make an oriented strand board out of these, or into wood fibers, and create a fiber board out of this. Fiber board contains a lot of glue, might be above 15% of the weight of the plate. Then we might use different products together, as for example plywood on the surface and massive wood in between. Or we might even combine this with cardboard parts for doors and other pieces. So wood can become a sort of wool as well, and then I could use, for example, cement as a binder and compress the whole thing, and then I would get cement bound wooden wool elements that are fire resistant and insulating and sound absorbing at the same time, but not very much, unfortunately. So you have certainly recognized that the tree trunk is much better in the longitudinal direction than in the tangential or perpendicular direction. This means compression resistance, it means tension resistance, and it means shrinking processes as well. Shrinking processes in the longitudinal direction are about 0.1%, and perpendicular they might get up to 3%. So we would, in most cases, try to use the wood in its longitudinal direction. And this is why it's called an isotropic material, so it has a preferential direction as compared to other materials like, for example, thermoplastics, which are anisotropic. They don't have a preferential direction.